lecture series on digital image processing. In the last class, we started our discussion on image interpolation and resampling. Today, we will continue with the discussion on the same topic, that is image interpolation and resampling, and today we will try to explain the concepts with the help of a number of examples. So, in the last class, we have talked about interpolation and resampling, and mostly we have discussed about the interpolation problems in case of one-dimensional signals. We have also seen that what are the desirable properties of the interpolation functions, and we have seen that it is the B-spline function which satisfies all the desired properties of interpolation. And we have seen the B-spline functions of different orders, and we have seen how these B-spline functions can be used for interpolation operations. In today's lecture, we will explain the interpolation in one dimension with the help of a number of examples. Then we will see the extension of this one-dimensional interpolation to two-dimensional images. Again, we will explain the image interpolation with examples, and then at the end of today's lecture, the students will be able to write algorithms for different image interpolation operation. So, let us see that what we mean by image interpolation operation. So, here we have shown a diagram which shows the sample values of an one-dimensional signal, say f t, which is a function of t. So, you find that in this particular diagram, we have given a number of samples, and here the samples are present for t equal to 0, t equal to 1, t equal to 2, t equal to 3, t equal to 4 and t equal to 5. The functions are given like this sample data. You find that the sample values are available only at 0, 1, 2, 3, 4 and 5. But in some applications, we may need to find out the approximate value of this function at say t equal to 2.3 or say t equal to 3.7 and so on. So, again here in this diagram you find that at t equal to 2.3, say somewhere here, I do not have any information, or say t equal to 3.7, somewhere here again I do not have any information. So, the purpose of image interpolation is by making use, or the signal interpolation is by using the sample values at these discrete locations, we have to reconstruct or we have to approximate the value of the function f t at any arbitrary point in the time axis. So, that is the basic purpose of the interpolation operation. So, whenever we go for some interpolation, we have to make use of certain interpolation functions, and this interpolation operation or the interpolation function should satisfy certain conditions. The conditions are: the interpolation function should have a finite region of support. That means, when we do the interpolation, we should not consider the sample values from say minus infinity to plus infinity. Rather, if I want to approximate the function value at location say t equal to 2.3, then the samples that should be considered are the samples which are nearer to t equal to 2.3. So, I can consider the samples at t equal to 1, I can consider the sample at t equal to 2, I can consider the sample at t equal to 3, I can consider the sample at t equal to 4 and so on. But for approximate the functional value, to approximate the functional value at t equal to 2.3, I should not consider the sample value at say t equal to 50. So, that is what is meant by finite region of support. Then the second property which this interpolation operation must satisfy is it should be a smooth interpolation. That means, by interpolation we should not introduce any discontinuity in the signal. Then the third operation, the third condition that must be satisfied for this interpolation operation is that the interpolation must be shift invariant. That is, if I shift the signal by say t equal to 5, even then the same interpolation operation, the same interpolation function should give me the same result in the same interval. So, these are what are known by the shift invariance property of the interpolation. And we have seen in the last class that B-spline interpolation functions satisfy all these three properties, which are desirable properties for interpolation. So, these B-spline functions are something like this. We have seen that for interpolation with the help of B-spline function, we use a B-spline function which is given by BIK. So, let me just go to what is the interpolation operation that we have to do. So, for interpolation what we use is say f t should be equal to some p I into b I k t, where I varies from 0 to say n, where p I indicates the ith sample and b I k is the interpolation function. And we have defined in the last class that this b I k can be defined as b I k, it can be defined recursively as t minus t I into b I k minus 1 t upon t I plus k minus 1 minus t I plus t I plus k minus t into b I plus 1 k minus 1 t upon t I plus k minus t I plus 1, where b I 1 t is given by, it is equal to 1 for t I less than or equal to t less than t I plus 1, and it is equal to 0 otherwise. So, find that when we have defined b I 1 t to be 1 within certain region and it is equal to 0 beyond that region, then using this b I 1 I can estimate, I can calculate the values of other b I k by using the recursive relation. And pictorially these different values of b I k, for k equal to 1 it is a constant, for b I 2 that is for k equal to 2 it is a linear operation, linear function, for k equal to 3 b I 3 is a quadratic function, and for k equal to 4 that is b I 4 it is a cubic equation. And we have said in the last class, so here you find that the region of support for b I 1 is just one sample interval. For b I 2 the region of support is just 2 sample intervals, for b I 3 it is 3 sample intervals, and for b I 4 it is 4 sample intervals. And we have mentioned in the last class that out of this the quadratic one, that is for value k equal to 3, it is normally not used because this does not give a symmetric interpolation. Whereas, using the other 3, that is b I 1, b I 2 and b I 4, we can get symmetric interpolation. So, normally the functions, the B-spline functions which are used for interpolation purpose are the first order, that is k equal to 1, the second order or linear, that is k equal to 2, and the cubic interpolation, that is for k equal to 4. And we have also said that these functions for k equal to 1, k equal to 2 and k equal to 4 can be approximated by B 0 1 t is equal to 1 for 0 less than or equal to t less than 1 and it is equal to 0 otherwise. So, only in the range 0 to 1 excluding t equal to 1, b 0 1 equal to 1 and beyond this range b 0 1 is equal to 0. Then b 0 2 is defined like this, that it is equal to t for 0 less than or equal to t less than 1 and it is equal to 2 minus t for 1 less than or equal to t less than 2 and it is equal to 0 otherwise. So, here again you find that for the values of t between 0 and 1, b 0 to t increases linearly. For t equal to 1 to 2, the value of b 0 to decreases linearly and beyond 0 and 2, that is for values of t less than 0 and for values of t greater than 2, the value of b 0 2 is equal to 0. Similarly, for the quadratic one, for the cubic one, b 0 4 is defined as b 0 4 t will be defined as t cube by 6 for 0 less than or equal to t less than 1. It is defined as minus 3 t cube plus 12 t square minus 12 t plus 4 divided by 6 for 1 less than or equal to t less than 2. This is equal to 3 t cube minus 24 t square plus 60 t minus 44 divided by 6 for 2 less than or equal to t less than 3. This is equal to 4 minus t whole cube divided by 6 for 3 less than or equal to t less than 4 and it is 0 otherwise. So, these are the different orders of a B spline function. So, here again you find that for value equal to value of t less than 0, b 0 4 t equal to 0 and similarly for value of t greater than 4, b 0 4 t is also equal to 0. So, these are the B spline functions using which the interpolation operation can be done. Now, let us see that how do we interpolate. Again I take the example of this sample data, where I have a number of samples of a function t and which is represented by f s t, and the values of f s t are present at t equal to 0, t equal to 1, t equal to 2, t equal to 3, t equal to 4 and t equal to 5. As we said that the interpolation function is given by this f t is equal to p I b I 1 t if I go for constant interpolation. Now, here b I 1 t, so when we had computed say b 0 1 t, we have said that this value is equal to 1 for t lying between 0 and 1 and this is equal to 0 otherwise. So, if I interpolate this particular sample data, say for example, I want to find out what is the value of the signal at say 1.3. So, this is the point 1 point t equal to 1.3. So, I want to find out the value of f t at t equal to 1.3. So, to do this, my interpolation formula says that this should be equal to f 1.3, this should be equal to p 0 into b 0 1 1.3 plus P1 B11 1.3 and so on. Now, if I plot this B01 1.3, just superimpose this on this particular sample data diagram, you find that B01 1.3 or B01t, the function is equal to 1 in the range 0 to 1 excluding 1. Similarly, P1 B11 1.3, the value will be equal to 1 in the range 1 to 2 excluding 2, and it will be 0 beyond this. So, when I try to compute the function value at t equal to 1.3, I have to compute P0, that is the sample value at t equal to 0, multiplied by this B01t. Now, because B01t is equal to 0 for values of t greater than or equal to 1, so this particular term P0 into B01t, this term will be equal to 0. Now, when I compute this P1 into B11 1.3, you find that this B11 1.3 is equal to 1 in the range 0 to 1 to 2 excluding 2, and beyond 2 the value of B11t is equal to 0. Similarly, for values of t less than or less than 1, the value of B11t is also equal to 0. Similarly, P2 B21, that value is 1 within the range 2 to 3. So, within this range B21 t is equal to 1, and beyond this B21 equal to 0. So, when I try to compute the value at point 1.3, you find that this will be nothing but P1 into B11 1.3, and this B11 1.3 is equal to 1. So, the value at this point will be simply equal to P1. So, in this case it is Fs1, and you find that for any other values of t within the range 1 to 2, the value of Ft will be same as F1 or P1. So, I can approximate this, or I can do this interpolation like this, that is between 1 and 2, all the values, the function values for all values of t between 1 and 2 will be equal to 1. Following similar argument, you find that between 2 and 3, the function value will be equal to F2. Between 3 and 4, the function value will be equal to F3. Between 4 and 5, the function value will be equal to F4, and it will continue like this. So, this is what I get if I use this simple interpolation formula, that is Ft equal to P1 Pi Bi1t. Similar is also the situation if I go for linear interpolation. So, what I get in case of linear interpolation? In case of linear interpolation, Ft is given by Bi2 Pi into Bi2t, where we have to take the summation of all these terms for values of I from I equal to 0 to n. So, what we get in this case? You find that we have said that Bi0t is nothing but a linearly increasing and decreasing function. So, if I plot B02t, B02t is a function like this, which increases linearly between 0 and 1. At 1, this reaches a value 1, and then again from t equal to 1 to t equal to 2, the value of B02t decreases linearly and it becomes 0 at t equal to 2. Similarly, B12t will have a function value something like this. It will increase linearly from 1 to 2, it will reach a value of 1 at t equal to 2, and again from t equal to 2 to t equal to 3, it decreases linearly. Then at t equal to 3, the value of B1 to t becomes equal to 0. So, here again if I want to find out, say for example, the value of function at say t equal to 1.7. So, I have the functional values at t equal to 1, I have the value of the function at t equal to 2. Now, at t equal to 1.7, I have to approximate the value of this function using its neighboring pixels. Now, if I try to approximate this, you find that using this particular interpolation formula, here again f 1.7 is to be computed as p 0, b 0 to 1.7 plus p 1 b 1 to 1.7. So, it will continue like this. Now, here you find that the contribution to this point by this sample p 0, by this sample value p 0 is given by this interpolation function b 0 to t, and by this the contribution to this point t equal to 1.7 by this sample f 1 or p 1 is given by b 1 to 1.7. Contribution to this point by the sample value f 2 is given by b 2 to 1.7, but b 2 to 1.7 is equal to 0 at t equal to 1.7, because b 2 to 1.7 is something like this. So, value of this function is 0 at t equal to 1.7. So, only contribution that we get at t equal to 1.7 is from the sample f 0 and from the sample f 1. Okay. So, using this I can estimate what will be the value of b 0 2 at 1.7. I can also estimate what will be the value of b 1 to 1.7. And in this particular case, we have seen a property of this B spline function, that is, we have said earlier that b I k t is nothing but b 0 k into t minus I. So, that is a property of these B spline functions. So, when I do this, you find that this b 1 to 1.7 is nothing but b 0 to, because this is t minus I and value of I is equal to 1. So, this will be b 0 to 0.7. So, if I simply calculate the value of b 0 2 for different values of t, I can estimate that what will be b 0 to 1.7. And in that case, the value at this location, that is f 1.7, will now be given by, if I simply calculate this. So, in this case f of 1.7 will be given by p 0 into b 0 to 1.7 plus p 1 into b 0 to 0.7, because this is same as b 1 to 1.7, where value of p 0 is equal to 0.5, which is the sample value at location t equal to 0, and value of p 1 is equal to 1, that is the sample value at location t equal to 1. Now, here you find that there is a problem, that if when I am trying to compute the value at t equal to 1.7, the contribution only comes from the sample values at t equal to 0 and t equal to 1. But this interpolation of this approximate value does not have any contribution from t equal to 2 or t equal to 3. So, your interpolation or approximation that you are doing is very much biased, because it is only considering the sample values to the left of this particular point. We are not considering the sample values to the right of this particular point t equal to 1.7. So, that is a problem with this basic interpolation formula. So, to solve this problem, what we do is, instead of using the simple formula, that is f t equal to summation p I b I k t, where I varies from 0 to n, we slightly modify this interpolation formula. We make, say, f star t is equal to p I b I minus s k t, where again I varies from 0 to n. And the value of s, we decide that for k equal to 1, that is when we go for constant interpolation, we assume value of s to be 0.5. For k equal to 2, that is for linear interpolation, we assume value of s to be 1, and for k equal to 4, that is for cubic interpolation, we assume value of s to be equal to 2. So, here again we find that I have not considered k equal to 3, because as we said that k equal to 3 gives you the quadratic interpolation, and in case of quadratic interpolation, the interpolation is not symmetric. So, what we effectively do by changing b I k t to b I minus s k t is that the interpolation function or the B spline interpolation function, we give this a shift by s in the left direction, while we consider the contribution of the sample p I to the point t for interpolation purpose. Now, let us see what we get after doing this. So, as we said that with k equal to 1, I take the value of s is equal to 0.5. So, in the formula that p I b I k t, if when I consider the contribution of sample p 0, in the earlier formulation we had to use the B spline function b 0 k t. Now, if k equal to 1, this is a constant interpolation. So, I have to consider b 0 1 t. Using this modified formulation, when I consider the contribution of point p 0, I do not consider the B spline function to be b 0 1 t, but rather I consider the B spline function to be b minus 0.5 1 t. Similarly, for the linear operation, when I take the contribution of point p 0 to any arbitrary point, along with p 0, I had to consider, as per the initial formulation, b 0 2 t. Now, using this modified formulation, I will use minus b minus 1 2 t. Similarly, for the cubic interpolation, again with p 0, I will consider the B spline function to be b minus 4 t instead of b 0 4 t. So, here you find that in this particular diagram, using this formulation, effectively what we are doing is, we are shifting the B spline functions by the value of s in the leftward direction. So, b 0 1 t, in the earlier case, we had b 0 1 t to be 1 between 0 and 1. So, b 0 1 t was something like this. Now, along with p 0, I do not consider b 0 1 t, but I will consider b minus 0.5 1 t, and minus 0.5 1 t is equal to 1 for values of t between minus 0.5 and plus 0.5, and value of b minus 0.5 1 t will be equal to 0 beyond this range. Similar is also the case for the linear interpolation, the linear B spline, and it is also similar for the cubic B spline, that is b I 4 t, and in this case it will be I minus 2 4 t. So, using this, let us see that how it helps us in the interpolation operation. So, as I said that for interpolation, when I consider the contribution of p 0 to any particular point, along with p 0, I will consider the B spline function to be b minus 0.51 t for constant interpolation. So, it appears like this, that for contribution of p 0, I consider b minus 0.51 t. To find out the contribution of p 1, I consider the B spline function to be b 0.51 t. Similarly, in case of linear interpolation, to find out the contribution of point p 0, I consider the B spline function to be b minus 1 2 t, and to find out the contribution of P1, I consider the B-spline function to be B0 2t and so on. Similar is also case for the cubic interpolation. Here again, to find out the contribution of say P0, I have to consider the B-spline function of B minus 2 4 t. To find out the contribution of P1, I have to consider the B-spline function of B minus 1 4 t. Find out the contribution of P2, I have to consider the B-spline function of B 0 4 t and so on. Now, let us see that using this kind of using this modified formulation, whether our interpolation is going to improve or not. So, let us take this particular case. Again we go for constant interpolation. Here again I have shown the same set of samples, and now suppose I want to find out what will be the value of the function at say t equal to 2.3. And for considering this, I will consider the equation to be P I into B I minus 0.5 for constant interpolation value of k is equal to 1 t, and I will take the sum for I equal to 0 to n. So, this will give me the approximate or interpolated value at t. So, again you find that coming to this diagram, as we have said that when I consider B I minus 0.5 t, okay, in that case B minus 0.51 t is equal to 1 between the range minus 0.5 to plus 0.5, and beyond this range B minus 0.5 t will be equal to 0. So, when I compute P 0 B minus 0.51 t for computation of this particular component, along with this sample P 0 which is equal to 0.5, I have to consider the Bezier function, the Bezier B-spline interpolation function as this, which is equal to 1 from minus 0.5 to plus 0.5. So, here again you find that because this B minus 0.51 t is equal to 0 beyond t equal to 1.5. So, this P 0 does not have any contribution to point t equal to 2.3, because at this point the contribution of this or this particular product P 0 B minus 0.51 t will be equal to 0. Similarly, if I consider the effect of point P 1 to t equal to 2.3, the effect of point P 1 will also be equal to 0, because the product P 1 B minus 1 P 1 B 0.51 t is equal to 0 at t equal to 2.3. But if I consider the effect of P 2 which is equal to 0.6 here, you find that for this the B-spline interpolation function has a range something like this, the region of support. So, this is equal to 1 for t equal to 1.5 to t equal to 2.5, and it is equal to 0 beyond this range. To find out the contribution of P 3 which is equal to 1.1, here again you can see that to find out the contribution of this particular point, the corresponding B-spline function, that is B 2.5 t, is equal to 1 in the range 2.5 to 3.5, and it is equal to 0 outside. So, even P 3 does not have any contribution to this particular point t equal to 2.3. So, at t equal to 2.3, if I expand this, I will have a single term which is equal to P 1 into B P 2 into B 1.51 t. So, where t is equal to 2.3, and the same will be applicable for any value of t in the range t equal to 1.5 to t equal to 2.5. So, I can say that using this formulation, what I am getting is I am getting the interpolation something like this. After interpolation, using this constant interpolation function after our modified formulation, the value of the interpolated function will be, say, from t equal to 0 to t equal to 1.5, the f t value of f t will be equal to f 0. Between 1.5 to between 0.5 to 1.5, value of f t will be equal to f 1. From point 1.5 to 2.5, the value of f t will be equal to f 2. From 2.5 to 3.5, the value of f t will be equal to f 3. From 3.5 to 4.5, the value of f t will be equal to f 4, and from 4.5 to 5.5, the value of f t will be equal to f 5. And this appears to be a more reasonable approximation, because what we are doing is, whenever we are trying to interpolate at a particular value of t, what we are doing is, we are trying to find out what is the nearest sample to that particular location of that particular value of t, and whatever is the value of the nearest sample, we are simply copying that value to this desired value of t. So, here for any point within this range, that is for t equal to 1 to t equal to 1.5, the nearest sample is f 1. For any sample from 1.5 to 2, the nearest sample is p 2 or f 2. So, this f 2 is copied to this particular location t, where t is from 1.5 to 2. So, this appears to be a more logical interpolation than the original formulation of interpolation. Similar is also case for linear interpolation. In case of linear interpolation, when I consider the value of p 0, what I do is, I consider b minus 1 to t, and b minus 1 to t is something like this. Where from minus 1 to 0, this increases linearly, attains a value of 1 at t equal to 0. Similarly, if when I consider the contribution of p 1, the corresponding Bezier interpolation function that I have to consider is b 0 to t, which is something like this. So, now if I want to find out what is the value at the same point, say 2.3, you find that to find out the value at point 2.3, the contribution of p 1 will be equal to 0, because the value of b 0 to t is equal to 0 beyond point t equal to t equal to 2. And by this, you will find that the only contribution that you can get to this point t equal to 2.3 is from the point p 2 and from the point p 3. Okay. And in this particular case, I will have f 2.3, which will be nothing but p 2, then b, because it is, I have to make it I minus 2 in I minus 1 in this particular case. So, this will be equal to b 1 to 2.3 plus p 2 into b p 3 into b 2 to 2.3, just this. So, the contribution of this point to this point t equal to 2.3 will be given by this value, and the contribution of point p 3 will be given by this value. And here you find that because the function increases linearly from 0 to 1 between t equal to 2 and t equal to 3, and it decreases linearly from 3 to 0, when t varies from 3 to 4. So, here you find that the value that we will get will be nothing but p 2 into the value of this function in this particular case will be equal to 0.7 plus it will be p 3 into 0.3. So, if I simply replace the value of p 2 which is equal to 0.6 and p 3 which is equal to 1.1, I can find out what is the value of f t at t equal to 2.3. So, similar is also the case for cubic interpolation, and in case of cubic interpolation you find that your region of supports will be something like this. Okay. Sorry. So, the nature of the region of support will be something like this, and again by using the same formulation, that is f t is equal to p I b I minus 2 in this particular case into k, value of k is equal to 4 t, I can find out, and taking the summation for I equal to 0 to n, I can find out what will be the value of f t for any particular time instant t or any arbitrary time instant t. So, by modifying these interpolation operations, we can go for all these different types of interpolation. Now, to explain this, let us take a particular example. So, I take an example like this. I take a function, say f, the function values are like this, that f of 0 so I take f of 1 is equal to say 1.5, I take f of 2 is equal to 2.5, I take say f of 3 is equal to say 3, I take f of 4 is equal to something like say 2.5, I take f of 5 is equal to again 3, f of 6 maybe something like 2.4, I can take f of 7 to be something like say 1, I can take f of 8 to be something like 2.5. And I want to find out the approximate value of this function at say t equal to 4.3. So, given these sample values, I want to find out what is the value of this function at t equal to 4.3. So, I want to find out f 4.3 given this sample values, and suppose the kind of interpolation that I will use is a cubic interpolation. So, I use cubic interpolation, and using these samples I want to find out the value of f 4.3. So, let us see that how we can do it. Here you find that f 4.3 can be written as, considering the region of support, this can be written as f 3 into b 1 4.3. So, you find that since this f 3 is nothing but p 3 in our case. So, this b I becomes b I minus 2. So, 3 minus 2 is equal to 1. So, I am considering b 1 4 and at location t equal to 4.3. So, this will be plus f 4 which is nothing but p 4 into b 2 4 4.3 plus it will be f 5 into b 3 4 at location t equal to 4.3 plus it will be f 6 into b 4 4 at location t equal to 4.3. Okay. Now, as we said that we have told that b I k t is nothing but b 0 k t minus I. So, just by using this particular property of the B spline functions, I can now rewrite this equation in the form that this will be equal to f 3 or p 3 into b 0 4, and this will be now t minus I is equal to 1. So, this will be b 3.3 plus f 4 into b 0 4 2.3 plus f 5 into b 0 4 1.3 plus f 6 into b 0 4, and this will be equal to 0.3. Now, you can compute the values of this b 0 4 3.3, you can compute the values of b 0 4 2.3, you can compute the value of b 0 5 1.3, and you can also compute the value of b 0 4 0.3 using the approximate analytical formula of b 0 4 t that you have given, and you have seen that this is nothing but a cubic formula of variable t. So, if I do this, you will find that, and using the sample values, this b 0 4 3.3, this gets a value of 0.057, b 0 4 2.3, this gets a value of 0.59, b 0 4 1.3, this gets a value of 0.35, and b 0 4 0.3 gets a value of 0.0045, and you can verify this by using the computation, the analytical formula that we have given. And by using the values of f 3, f 4, f 5 and f 6, if I compute this equation, then I get the final interpolated value to be 0.7068, sorry 2.7068. Now, if I do the same computation using constant interpolation, and as I said that the constant interpolation is nothing but a nearest neighbor interpolation. So, when I try to find out the value at f 4.3, the point t equal to 4.3 is nearest to point t equal to 4 at which I have a sample value. So, using nearest neighbor or constant interpolation, f 4.3 will be simply equal to f 4, and which in our case is equal to 2.5. Whereas, if I go for linear interpolation, again you can compute this using the linear equations that we have said, that using linear interpolation the value of f 4.3 will be equal to 2.65. So, you find that there is slight difference of the interpolated value whenever we go for constant interpolation, or we go for linear interpolation, or we go for cubic interpolation. So, using this type of formulation, we can go for interpolation of the one dimensional sampled functions. Now, when we go for the interpolation of image functions, you find that images consist of a number of rows and a number of columns. Now, the interpolation that we have discussed so far, these interpolations are mainly valid for one dimension. Now, the question is, how do we extend this one dimensional interpolation operation into two dimension, so that it can be applied for interpolation images as well. So, in case of image, what we will do is, as the image is nothing but a set of pixels arranged in a set of rows and in a set of columns. So, let us consider a two dimensional grid to consider the image pixels. So, I have the grid points like this. So, in case of an image, I have the image points or image pixels located at this location, located at this location. So, these are the grid points where I have the image pixels. So, it is something like this. So, I say this is location 0 0, this is location say 0 1, this is location 0 2 and so on. So, that I have this as the 0th row, this as the 0th column, and similarly I have row number 1, row number 2, row number 3, row number 4 and column number 1, column number 2, column number 3, column number 4 and so on. Now, given this particular situation, so I have the sample values present at all these grid points. Now, given this particular pixel array, which is again in the form of a 2-dimensional matrix, if I have to find out what will be the pixel value at this particular location. Suppose this is say location 4 4, let us assume this is at pixel location say 4 5, 4th row 5th column. This may be a pixel location say 5 4, that is 5th row 4th column, and this may be the pixel location say 5 5, that is 5th row and 5th column. So, at these different pixel locations I have the intensity values or pixel values, and using this I want to interpolate what will be the pixel value at location say 4.3 and say 4.2. So, I want to compute what will be the pixel value at this particular location 4.3 and 4.2. So, now we find that the earlier discussion what we had for interpolation in case of 1 dimension, now that has to be extended for 2 dimension to get the image interpolation. Now, the job is not very complicated, it is again a very simple job. What we have to do is, I have to take the rows one after another, I also have to take the columns one after another. So, first what you do is, you go for interpolation along the rows and then you try for interpolation along the column. And for this interpolation again I can go for either constant interpolation or I can go for linear interpolation or I can go for cubic interpolation. But now, because our interpolation will be in 2 dimension, so the kind of interpolation, if it is a linear interpolation, it will be called a bilinear interpolation. For cubic interpolation, it will be called a bicubic interpolation. So, let us see that what will be the nature of interpolation if I go for a constant interpolation. So, effectively what we will do is, so in this particular case we will interpolate along the row 4, we will also interpolate along the row 5. So, we will try to find out what is the value pixel value at location 4 4.2, we will also try to find out what is the pixel location at point 5 4.2. So, once I have the pixel values interpolated values at this location and this location, that is 4 4.2 and 5 4.2, using these two sample values I will try to interpolate the value at those this location 4.3 4.2. So, simply extending the concept of 1D interpolation to 2D interpolation. Now, what will be the nature of this interpolation if I go for constant interpolation? So, as we said that constant interpolation simply takes the nearest neighbor and copies to the particular the arbitrary location which does not occur on the regular grid. So, at this location I have a pixel value, at this location I have a pixel value, at this location I have a pixel value, at this location I have a pixel value. Now, if I want to find out what will be the value of the pixel at this particular location, what I do is I simply try to find out which is the nearest neighbor of this particular point, and here you find that the nearest neighbor of this particular point is this point. So, all the points which are nearest to this particular point. So, within this square all the pixel values will get the value of this particular pixel. So, it will be something like this. Similarly, all the pixels, all the points lying within this region will get the pixel values of this particular region. Similar is the case here and similar is the case here. When you go for bilinear interpolation, when I try to interpolate the pixel at any particular location like this, so again here in case of bilinear interpolation, if I want to find out the pixel value at any particular, any arbitrary grid location, so something like this, say somewhere here, what I have to do is I have to consider this pixel and this pixel, do the bilinear interpolation to find out the pixel at this location. I consider this pixel and this pixel, do bilinear interpolation to find out the pixel value at this location. Then using this and this, doing bilinear interpolation along the column, I can find out what is the pixel value at this particular location. And the same concept can also be extended for bicubic interpolation. So, by this we explain how to do interpolation, either constant interpolation, which we have said is also the nearest neighbor interpolation. We can go for linear interpolation, in case of image it is bilinear interpolation, or the cubic interpolation, in case of image it is bicubic interpolation. So, where you have to do interpolation both along the rows, and after the rows you can do it along the columns. It can also be reverse. First you can do the interpolation along column, then using the interpolated value along 2 or more columns, I can find out the interpolated value on any row location which does not fall on any regular grid point. Okay. So, now let us see that what are the results. These results we had already shown in the last class. So, you find that the first one is interpolated using nearest neighbor interpolation, and as we have explained that because the value of the nearest pixel is copied to all the arbitrary locations. So, this is likely to give a blocking artifact, and in this nearest neighbor interpolated image you also find that those blocking artifacts are quite prominent. We have also seen the output with other interpolation operations. We have shown the output with linear B-spline interpolation. We have also shown the output with cubic B-spline interpolation. Okay. So, this is the case with rotation. Again, when you rotate, if you do not interpolate, you get a number of patches, black patches as is shown in the left image. If you go for interpolation, all those black patches will be removed and you get a continuous image as is shown in the right image. Now, this interpolation operation is useful not only for this translation or rotation kind of operations. You find that in many other applications, for example, in case of satellite imagery, when the image of the Earth's surface is taken with the help of a satellite. Now, because of Earth's rotation, the image which is obtained from the satellite, the pixels always does not fall on regular grids. So, in such cases what we have to go for is to rectify the distortion or to correct the distortion which appears in the satellite images, and this distortion is mainly due to the rotation of the Earth's surface. So, for correction of those distortion, the similar type of interpolation is also used. Thank you.